Here are two matrices that look almost the same on paper. The first is 4 times the identity, a diagonal matrix with 4 and 4 on the diagonal and the zeros off diagonal. The second has 4 and a 1 on the top row and a 0 and a 4 on the bottom row. Let's check their invariants. Both have characteristic polynomial lambda minus 4 squared, so both have eigenvalues 4 and 4. Both have trace 8, the sum of the diagonal entries. Both have determinant 16, 4 times 4. By every standard numerical invariant, they look identical. So they should be similar, right? But they're not. No invertible matrix M will ever connect them through the relation M inverse AM equals B. The reason? The first matrix is already a scalar multiple of the identity, so any similarity transformation leaves it unchanged. The second matrix is a Jordan block, with a non-zero 1 above the diagonal, and no change of basis can erase that. Same eigenvalues, same trace, same determinant, but two different worlds. Let's figure out what's going on here. Recall the definition. Two matrices A and B are called similar when B equals M inverse times A times M for some invertible matrix M. When a matrix has distinct eigenvalues, life is simple. Every such matrix is similar to the diagonal matrix lambda built from its eigenvalues. One eigenvalue set gives one similarity family, but the moment eigenvalues start to repeat, that clean rule breaks down. A single set of eigenvalues can split into multiple disjoint similarity families that never talk to each other. Picture the universe of all 2 by 2 matrices whose eigenvalues are both 4. Naively, we'd expect one big similarity family. Instead, it splits into 2 disjoint pieces. Family 1 is a lonely singleton containing only the scalar matrix 4 times the identity. Family 2 is a crowd represented by the Jordan block with 4, 1 on top and 0, 4 on the bottom. Nothing crosses between them. Let's prove why 4 times the identity is stranded all by itself. Take any invertible matrix M and conjugate 4i. We get M inverse times 4i times M. Now pull the scalar 4 out in front. That gives 4 times M inverse times I times M. The identity matrix disappears, leaving 4 times M inverse times M, which is just 4i again. Scalar matrices commute with everything, so conjugation cannot move them. No matter what M you pick, you come right back to 4i. Family 1 has exactly one member, that's the singleton. Now meet family 2's representative. The Jordan block J, with 4 and 1 on the top row and 0 and 4 on the bottom row. A Jordan block is an upper triangular matrix with a repeated eigenvalue on the diagonal and ones just above the diagonal. Let's check its invariance. The trace is 4 plus 4, which equals 8, the same as before. The determinant is 4 times 4 minus 1 times 0, which equals 16, again the same. And the characteristic polynomial is lambda minus 4 quantity squared, giving repeated eigenvalues of 4 and 4. So on paper, J shares every invariant with 4 times the identity. But here is the crucial difference. J is not a scalar multiple of the identity. That off-diagonal one breaks the symmetry, and it means the proof we just did for 4i doesn't apply. Conjugation can move J freely, producing a whole family of similar matrices rather than just one. Family 2 isn't just a Jordan block. Let's meet some of its other members. Consider the matrix with rows 5, 1 and a negative 1, 3. Its trace is 5 plus 3, which equals 8. Its determinant is 5 times 3 minus 1 times negative 1, that's 15 minus negative 1, equals 16. So the characteristic polynomial is lambda minus 4, all squared. The same story plays out for the matrix with rows 4, 0, and 17. 4, trace 8, determinant 16, eigenvalues 4 and 4. Both of these matrices look nothing like the Jordan block, yet both are conjugate to it. Family 2 is huge. So what's the real invariant separating these families? Count the independent eigenvectors. An eigenvector for eigenvalue 4 solves A minus 4i times x equals 0. Case 1. A is 4i. Then a minus 4i is the 0 matrix, and every vector in R squared works. We get two independent eigenvectors, say 1, 0 and 0, 1. Case 2. A is the Jordan block. Then A minus 4i has 0, 1 on top and 0, 0 on the bottom. That forces the second coordinate to be 0, so the eigenvectors only span the direction 1, 0. We get exactly one independent eigenvector, 2 versus 1. That's the split. Why can't the families overlap? Under similarity, eigenvectors transform by the rule x maps to M inverse x. That transformation is invertible, so it preserves linear independence. This means the number of independent eigenvectors, called the geometric multiplicity, is a similarity invariant. A matrix with two independent eigenvectors can never be similar to one with only one. That's exactly why 4 times the identity and the Jordan block live in separate worlds. The lesson: eigenvalues alone don't classify matrices up to similarity. You also need to know how many eigenvectors actually exist. This splitting is exactly what Jordan normal form tracks. Each Jordan block of size bigger than 1 records a missing eigenvector. Family 1, the diagonalizable case, gets the diagonal form 4 times the identity. Family 2, the defective case, gets the Jordan block with that extra 1 above the diagonal. The full classification uses eigenvalues plus geometric multiplicities plus Jordan structure. Every square matrix has a Jordan form, and the Jordan block is the most diagonal-like representative of every defective family. Eigenvalues set the stage. Eigenvectors decide the world.